Welcome back to the Saga Tech Gates. In this video, we will discuss various abstraction levels in Verilog. So, abstraction level refers to the different ways in which the hardware or structure can be designed or described. So, in Verilog has a capability of designing a model in several coding styles. As we know that if you want to describe any digital circuits in terms of model only, so everything is a model in a Verilog. So it has a capability of designing a model in a several coding styles. So we can describe that model in a various ways. So depending on the needs of a design, the internal of each module can be defined at various level of abstractions. So means we can define model in various ways. So we have 4 levels. In first one, behavioral and algorithmic level. So behavioral modeling is the highest level of modeling, highest level of abstraction in Verilog. So it focuses on what circuit should do instead of how it is implemented. So in a behavioral modeling style, we'll focus on what circuit do instead of how it is implemented. So it uses a construct like a similar software programming language like if, else, and case statement. So especially in Verilog, we'll use a procedure blocks like always to describe a circuit behavior, especially in a behavioral modeling style. So another modeling style is a data flow modeling. So data flow modeling describe the behavior of a circuit in terms of how data flows between a variable using a continuous assignment statement. So we have a continuous assignment statement in a Verilog. By using those statements, we can describe the hardware behavior in a data flow modeling. So another modeling style is a gate level or structural level. So in gate level modeling is a low level abstraction in a Verilog, where a circuit described using a basic logic gates like AND, OR, XOR, XNOR, NOR, and NAND. So these all basic gates are known as a primitives. So by instantiating these primitives, we can design that a digital circuit. We can describe the behavior of a digital circuit. So in a structural modeling, describe a digital circuit by explicitly specifying its interconnection between various modules, maybe a gates, etc. So for example, if you want to design a full adder by using off adders, so we instantiate 2 off adders in the full adder. So it is a structural modeling style. So another is the switch level. So in switch level modeling, it is the lowest level of abstraction in a Verilog, whereas the behavioral is the highest level of abstraction in Verilog, where this switch level is the lowest level of abstraction in Verilog. It allows the designer to describe the digital circuit at a transistor level using a MOSFET switches. Sometimes you may use different abstraction levels to describe the same hardware. Like for example, so to describe that whole system, we'll use a mix of these also. So for advantage of mixing of those abstraction level like design flexibility, optimization, and modularity. For example, in case of high level abstraction, so it speed up the functional modeling. So the high level abstraction speed up functional modeling. So whereas the low level allows a fine tuning of performance, area, and power. So for example, if you want to go for optimization of a particular model, then we will use a low level abstraction. In some cases, like speed up that functionality of a behavior, then we can use a high level of abstraction. So modularity. So different models can be designed at a different abstraction levels depending on the complexity and the design style. Design stages also. Right? So sometimes you may mix these abstraction levels also to define to describe the system behavior. Now see some examples. Now see, it is a simple off adder. Now see, it is a simple off adder. So it is a truth table for off adder. So AB as the input, sum as a output, a carry is the output. Now if you see the simple truth table, sum is the XOR, then carry is the AND gate. Now see this AB, the sum can get by performing the XOR of AB, carry can by performing AND of AB. The simple, just I'll describe this off adder using a different modeling styles. Now see, now in this case here, if we observe, here this offered this is a simple circuit diagram. So in gate level modeling, we use two gates here, XOR gate and AND gate. So now module name and this inputs and outputs, this declaration of those input and output ports. Okay, these are the ports. We will declare this AB as the input and some carries the output. Now here use the two gates. One is XOR and another is the AND gate. So XOR, so just I'll instantiate this. I'll instantiate these primitives. So by using this XOR, instance name and sum as the output A comma B. Okay, these are the two input, this is the output. Same way, so I'll use AND gate and Z2, this instance name Z2. So just I'll instantiate this primitive and, okay, Z2, this carry as output and AB as input. So now by using these primitives, we can describe this half adder. So this modeling style is known as a gate level modeling. Whereas in the data flow modeling, so in data flow modeling, we'll use a continuous assignment statement like, okay, assign. By using a keyword assign, we'll write the continuous assignment. So same module of adder, ports, input and output port declaration. Now we'll use this continuous assignment statement. So assign sum equal to A XOR B. So in this, we are just like a Boolean expression. In data flow modeling, just we'll write a Boolean expression. So how data is moving from one variable to another variables, okay? Like that, how data flows between the variables, we'll describing, okay? By using this continuous assign statement. So assign sum A XOR B and assign carry A and B. Just a simple Boolean expression, but we'll use a continuous assignment statement by using a keyword assign. So we'll discuss each and every abstraction levels like a data flow, behavioral, gate level in detail in further videos. Right, in a behavioral modeling, here just it focus on what the system do instead of how it is implemented. So by using a simple construct, if else, case, for, and also in Verilog we'll use a procedure block known as like always. So simply, so here module name, ports, declaration of those ports as input and outputs. So always, so we'll discuss about these constructs later. Just for understanding, just see this example, always at the rate A comma B. Whenever AB changes, then we trigger this block. So whenever AB changes, then this block will execute. This is the procedure blocks. So now begin and these statements are like sequential statement. So sum A XOR B, then carry A and B. So we are describing the behavior of this off adder by using this construct always. So now these are various ways we can write, okay, we can define a model for this off adder. Now see, this is a simple full adder, sum A XOR B XOR Cn and a carry AB plus BCn ACn. So like the same truth table we can by using K-map we'll get this expression. Just for understanding purpose I'm giving, I'll discuss all these in detail in the coming lectures. Now this is a simple circuit diagram in terms of gates for a full adder. Now this is a behavioral modeling style. So here just we'll describe the behavior, not internal structure, how gates are connected, what are the gates used to, okay, to describe this full adder. We didn't, just I'll describe the behavior. So module name, ports are declared as a ports, okay, input and output. So whenever if you use any variable in always procedure block, that LHS should be a reg. We'll discuss all this, okay. So output reg sum comma carry, because this sum carry as LHS in the procedure block, those should be declared as a reg. So always at the rate at this is the star means if anything changes in the RHS, it will execute. So if A changes or B changes or Cn changes, we can write this always at the rate A comma B comma Cn also. So always at the rate star begin and end. So carry sum. Already we discussed various operators used in the Verilog, okay, concatenation operator. So better you just see that video if not, okay. So carry sum is equal A plus B plus C. Just will describing the behavior of this full adder. So now in this data flow modeling, same module name, ports, input and outputs. By using a continuous assignment statement, we'll describe this. So just sum is equal to A XOR B XOR C. Now C carry is equal to A and B or B and C and or A and C. Just it is a Boolean expression. We just will write a Boolean expression as a continuous assignment statement. So in gate level modeling, now see here a module name, ports as declared as input and output. So these are the intermediate signals we use it to connect different entities in our system. Already we discussed this concept wire and range in detail in the Verilog data types. If not, please visit that video. Okay, right now see here, simple, we are described the full adder by using in terms of primitives gates. Now here XOR gate. So just I instantiated this XOR gate having two inputs A comma B and two inputs, then output here like sum. So we can represent as a W1, that is the intermediate signal W1. Now see this XOR gate. So now XOR gate, the output is a sum, then it has a two input. One is the output of this XOR gate, that is a W1. We can see this is the W1 output of first XOR gate as input of a second XOR gate W1 and a C in. So like here AND gate. So now AND. So now simply we use gates to describe the behavior of a full adder. How we are instantiating those gates, how they are connected. So by the output of one gate as the input of this, like that we'll connect these gates. So in gate level modeling, we'll use a primitives to represent the behavior of the digital circuits. Like the same way here carry also now. So output of this AND gate and output of this AND gate as the input for this carry. So W2 and W3 as a inputs. So how do I get a W2 here? How do I get a W2? So W2 as a, now see two inputs. Okay, A and B. This is the A and B, one AND gate. A and B as the input and W2. So A and B as the input, W2 as the output. So this is the W3. How do I get a W3? So now output of this, okay, this XOR. So one W1 and here this is C in. Okay, W1 and C in as the input, then we'll get W3 as the output. So like we can describe. Now see another example, a simple mux. So this is a schematic of 2:1 mux. So having two inputs, one selection line. So based on the selection line, that output is maybe connected to I0 or I1. If selection line is 0, then Y is connected to I0, Y equal to I0. So if selection line is 1, then Y is equal to I1. This is a simple Boolean expression for this mux. So Y is equal X bar I0 plus S I1. So S bar, so for example, S is equal to 0. So 0 prime is 1. 1 into I0. So Y is equal to I0 plus 0 into I1 0. So now Y is equal to I0. For example, S is equal to 1. Assume that. So 1 bar. 1 prime means 0. 0 into something 0. Then we'll get Y is equal 1 into I1. Y equal to I1. This is a simple Boolean expression. Okay. To describe this, to represent this 2:1 mux. So this is a logic diagram. Clear? Simple S bar into I0. S into I1, this is a simple OR gate. This is a simple logic diagram of 2:1. So these are the various ways we can describe this mux. So this is a simple behavioral modeling style. So module name and the ports output, and these are the inputs. Y as output, I0, I1 as input. Just I'll declare those as a input and output. So now simple, I'll describe the behavior by using this procedure block always. In case of behavioral modeling, like and software language will use like if else case for loop, like that. Same way we can use here also, right? So we concentrate on only behavior of the circuit, okay, not internal structure of the circuit. So always at the rate I0 or I1 or S. If anything changes, then this block will trigger. This block will execute. So begin and end. If S is equal to 1, then Y equal to I1. If S is equal to 1, Y is equal to I0. Else Y is equal to I0. This is a simple behavior of a circuit by using this if else statements. So same way data flow modeling. So by using continuous assignment, assign Y is equal, if S is equal to 1, see Y is equal to I1. If S is equal to 0, then we'll execute this block. So Y is equal to I0. And there is a conditional operator. Already we discussed in detail all operators in a Verilog. So if S is 1, it is a true, then this is a true expression. Y is equal to I1. If S is false, 0, then Y is equal to I0. So like that, we can use a continuous assignment to describe the digital circuit in a data flow modeling. Whereas this is the gate level modeling. So now these are the three gates. By using these basic gates, we can describe. Now here AND gate and this we need one NOT gate also to get S prime. So we'll use NOT gate. So S bar here simply. So AND gate, two AND gates and NOT gate and OR gate. By using these gates, we can describe this 2:1 mux. Just for idea purpose, I mentioned these examples. So we'll discuss each and every abstraction levels in detail in further lectures, in further videos. So from behavioral to the switch level, we'll discuss in detail of each abstraction level in Verilog in later videos. So thank you very much. I hope you understand what are the various abstraction levels. Just we want to know the list only. Okay, what are the various abstraction levels are available in Verilog? Nothing but how many ways we can define a module in a Verilog. Thank you very much.